There we go. All right, so like we were talking about, we're going to get into the next part, which is series circuits. And series circuits are pretty simple. And series circuits are probably the most important because even if you have a parallel circuit problem, mostly what we do is we determine what part of the parallel circuit is a failure, and then we basically test that section as a series circuit. So it all comes back to series circuit testing. But typically what I like to do is do just a bit of review to make sure you know the perspective of what we're talking about. So where we left off, we were talking about testing voltage, amperage, and resistance. And then you went and did a whole bunch of tests, so you should feel pretty good on that. But you may not feel amazing about what the real life effects are, or like what you'd actually run into. So let's kind of summarize that. So everybody should know by now, the automotive system is basically a 12-volt system. Now we say 12, but it's 12, but like it's 12.6 if it's fully charged. It's 13 point something if it's running. It might even be 14 point something if it's running, but we're still going to call it the 12-volt system. So generally, the 12-volt number is going to be fairly consistent. Okay, so if we have a problem in the circuit, it's most likely not because our 12-volt source is no longer 12 volts. So to put that into perspective, what I mean by that is if you had a battery that was fully charged at 12.6 and it discharged and discharged and discharged, and you ended up at, let's say, 6 volts, mathematically, your 6 volts with the same resistance would mean you'd have half the amps, if that makes sense. So if you were to visualize that, the 3 people and you got ohm with the rope. Well, if ohm with the rope was pulling the same, but volt pushing the amp through started pushing half amount, no longer 12-volt push, but only a 6-volt push, logically you'd have half the movement of amp if you just visualize it. So while that's true, we don't really talk a lot about that because if you had a battery that went from 12 volts to 6 volts, you're not really troubleshooting the circuit. Like at that point, you'd be like, oh, the car has a dead battery. How would you know if it has a dead battery? You've had dead batteries before, I assume. Did you start testing the wires to the headlights because the headlights were dim? Because that wouldn't be a good diagnosis. You'd be like, oh, everything in the car electrically isn't working. Everything is dim, or the car won't start. The windows, that's one of the first things I'll do. If I think a battery's dead, I'll jump in, I'll turn the key on, I'll put the windows up and down, I'll run a bunch of electrical things, maybe do the wipers and just be like, is this battery low? Because if the battery's low, the windows are slow, the wipers are slow, the lights are dim, but everything together, right? So the first thing when you jump into this vehicle is determine, does it seem like it's a source voltage issue? And if no, because some lights are bright and the power windows work well and all that, but like you have one dim headlight, then we're not really worried about the source voltage anymore. Does that make sense? So now we're on to more than likely rust, corrosion, debris. That's stuff that happens from the vehicle being used. And that's, where cars are a bit different than, household electrician type of work. The car is going down the road. A lot of the wires are outside the vehicle, so they're getting splashed and they're getting, in some areas salt, and we're really testing these things. So now that could sort of happen in a house, but like really the wiring should be in conduit and a little bit more protected in a home. Or if it's like if it's inside the wall, there shouldn't really be damage to the wiring inside the wall of a building. But in a car, there's a lot of moving stuff and vibration and things. And so we tend to see a little bit different stuff in the vehicles. And it also tends to be a little more, like in a lot of ways, just a little harder to figure out because you can't see where the wires go, which you can't if they're behind drywall. But if you have wires that are in a conduit in a commercial building, you can be like, oh, it starts there and it goes there. And if there was damage to the wires you'd see probably damage to the conduit with your eyes. On the car, not so much. You know, sometimes you will, but a good example would be on Duramax. When I used to work on Duramax all the time, there was this part on the Duramax diesel engine where this harness came over this bracket. And right there you'd look and it looked fine, but then, you know, it'd run into various issues, glow plug circuit codes or problems with injectors or problem with sensors. And you'd be like, it seems like an electrical issue. And you'd look right there, and I swear you'd look at it and you'd be like, it's fine. But actually what was interesting was it was run really tight, and the vibration would have whatever wires happened to be on the bottom would actually rub up against this bracket, and it would chafe the insulation off. And when it chafed the insulation off, then it would be shorted to ground, and it would cause, you know, all various numbers of various different faults. And then even if it wasn't shorted to ground, it chafed the insulation off, then it would corrode and end up with high resistance. And so you'd be like, I don't see any issues. But then sure enough, on the bottom side where you can't really see it, there's all these various problems. And so they could be much harder to diagnose, I think. And so if we think about a thing, let's make, like right here, we're talking about various lights. Let's just say the headlight. The headlight receives power from dedicated circuits. So that means, you know, maybe we have the headlight fuse and it goes to the headlight relay and through the headlight switch. And eventually it's going to go to the actual headlight bulb itself. If that bulb has an issue, it could be the bulb, we agree? But it could also be a problem in the circuit. So if that headlight is dim, probably I would suspect actually it's not the bulb. Bulbs don't really fail like that. Typically if a bulb fails, the filament inside the bulb it blows up and then it's a bulb that's out. And sometimes the filament's kind of broken, it'll like flicker and you might bang on it and it might work or not work. But if it's dim, I'd more be thinking, there's a problem in the circuit. When I say the circuit, I'm just talking about those wires that feed that headlight bulb. So if you're a DIY person and you have a problem, you tend to like want to look at all the wiring. I wouldn't do that. I would just really focus on the wiring that would have to do with that specific bulb being dim. Make sense? Go ahead.
So if you had that dim bulb thing,
yeah,
to diagnose it, you wouldn't
sure.
look at like the whole. You like it's let's say it's like 4 wires.
Mm-hmm.
You just chase those 4 wires and see what the fault is.
Ideally, if you knew where those wires went and like let's say you start at the bulb, right? The bulb is the problem, so logically we probably start there. Then you could say like, let me look at the ground side and then let me trace it back to this power source. But the problem is if you actually open the hood of the car, you can see like the headlight there, and then it goes into this conduit of wires, and then that thing disappears into nothing, you know? So I don't know that I'd really spend a lot of time looking in the underhood wiring because there's so much and so many different wires and so many different circuits, you know, whereas sometimes on the board, you know, we're dealing with just like a few wires. It's very simple. When you get out on the car, there's wires everywhere. So if you can see it, cool. But what I see a lot of brand new people is they'll like just start checking any wires that they see and they'll be like, oh, I see a thing here and a thing here. And I'd be like, but you don't even know if those wires have anything to do with the headlight. I probably do like a basic visual for what you can see that you know has to do with the headlight, and maybe something if it's obvious, of course. But after that, your visual inspection doesn't get you anything, you know. And that's where I see a lot of people kind of run out of gas. They typically will look and they'll find corroded things and they'll just be like cleaning connectors and being like, yeah, I cleaned a connector. Then I look and I'm like, I don't know that connector has anything to do with the headlights. Like, get focused. See, so we want to focus our diagnosis on the actual circuit for the headlight, which means pretty quickly we're no longer doing a visual. We're looking at wiring diagrams and we're finding out everywhere the circuit goes, right? So if it comes from the fuse, goes on one side to the switch, to the relay, to this connector, to the bulb, we're going to want to choose at which of those points are we going to do the test, not just keep doing an overall visual, if that makes sense. And then let's say, obviously it's got a dedicated circuit on the positive, and then typically the ground comes from the connection at the chassis. Now, that's not always the case. Sometimes we'll take a ground and we'll send it all the way to the load. But more commonly, the positive is on its own dedicated circuit. And then after the bulb, we're just going to do some short little wire to get it just to a chassis ground, or to, if it's a headlight, maybe to the radiator support or to the inside of the fender or something. And so just to give you the perspective, if we have a problem with a bulb or with any type of a load, a lot of times we're dealing with positive side issues because the power side has to come through all this stuff and go a lot further, whereas the ground a lot of times is short and just has to go to chassis. Now, that doesn't mean it can't be a problem with the ground. It just means if there's 10 feet of positive circuit and there's 1 foot of negative circuit, there's a good chance it's probably going to be on the positive. But the cool thing is, it's not really hard to tell. Go ahead.
Sometimes with like low voltage stuff, you'll see like 3 wires or 4.
Mm-hmm.
Is there like a common rule, like black is ground or green is ground and red is hot?
That's a pretty nice, like in a home, that's great because I found out the hard way. Okay, so I'll help you understand where I'm coming from. The shop was slow one day, and where I grew up there was snow, and when it was kind of dead, there wasn't that much going on, and a truck came in. You know, it was in the back of the pickup truck when it was snowing outside? Snow. Why not take the snow, pack it into a snowball, and throw it at your friend? I mean, give me one reason why I shouldn't do that. That sounds fun in the shop. The one reason would be I accidentally hit the inspection, like the smog machine. I hit the monitor. I tried to throw it at a friend, and the snowball exploded in the monitor. And actually, that's how we do our inspections and our smogs and stuff. And it shut off immediately, and it didn't work. And I was like, oh no, I'm in trouble. And the snow, I didn't even hit the guy. I just hit the inspection machine. So when I looked at that, I was like, oh, something got messed up. And when I was trying to really figure it out, I was looking at some of the wiring, and I was like, oh, the black wire, that must be the ground. And so for one reason or another, I don't exactly remember why, but I was messing with the wiring trying to get to figure out, and I thought the black would be the ground. And so I wired the black to ground, and the black is definitely not ground in houses and shops and dealerships. In those, the bare wire is ground, or if it happens to have insulation, it's more likely to be green. So black in the car is probably ground, but in a home, it's probably green or bare wire. Black in a house is the hot wire, so you may say the power wire. And then you got a white wire in there, and I'm like, what? Don't know what the white wire is. That's the neutral. So there's standards on the home side of things. Black is hot, white is neutral, green is ground, or bare is ground. But then the thing is, if you get into other types of wiring, sometimes red is also hot. On a car, depends on the manufacturer. Black for ground would be great. Green for ground is not that uncommon. Black with a white stripe is also fairly common, but there's many, many instances where it can be different colors. I would not suspect any ground to ever be red, but a lot of wires are a lot of different colors because we've got so many circuits, we run out of colors. So next thing you know, we're using different colors with different stripes and different things. So sadly, it's a good point. You can't really assume just looking at the color. You have no choice but to go over and look at the wiring diagram and actually understand the circuit and then be like, oh, that particular wire is the ground and that particular connector carries it. And so when we get actually onto it, it becomes a lot more, I don't know, it's not really difficult, but it's just more time consuming. You can't just look at it and be like, oh yeah, it works like this. You got to actually look it up.
So you have to look at the wire diagram.
You have no choice. Yeah, you really have no choice. Yep. And so if we think about the ground side, metals corrode, an area where the chassis is drilled or tapped, we might have a bolt installed. So that would be like an eyelet, the little round thing with the wire on it, and we're going to bolt it down. Well, what if that becomes rusty? Well, what I can tell you is rust is not a very good conductor. So you had a nice clean metal on metal contact, and now you have, due to rust and corrosion and time and vibration, now you have rust, corrosion, maybe a little bit of an air gap, maybe that whole bolt and all the threads are rusty. Now you have added resistance that used to be clean metal on metal. Now it's metal on rust, on salt, on corrosion. That's going to add resistance. Now, if we add resistance, that resistance is going to consume the voltage in a way where the load won't consume the full voltage anymore. So if you remember, like last week, what we talked about, the load should consume basically all the voltage, minus a few little pennies here and there along the way, across a connector, maybe across a switch, maybe across a little bit of the wire, depending on how long the wire is, right? So if we had $12, we're expecting to have that load consume like $11.97. Now you have a corroded ground, and that ground is like, hey, you know what? I'm going to take 6 of these volts. That leaves only 6 volts for your load. And so therefore your bulb is dim, and the whole issue is probably unwanted resistance somewhere in the circuit. But unlike the boards, it's not going to be a resistor that we put in to do an experiment. It's going to be like corrosion, rust, bad connection, like that's what it's talking about. If the ground is bolted to the chassis and it gets corroded, that's going to be added resistance right there. What you don't really want to do is just be like, oh yeah, I need to like take apart all these grounds and clean them, because you're not even sure that ground has to do with the headlight, right? So again, we refer back to the diagram when we say, which ground grounds the headlight? And then rather than just with your eyes going over and yanking it apart and cleaning it and putting it back together, not that that's bad, but you want to think like a doctor. The customer, the patient, the car, whatever comes in, you don't want to be like, oh, well, let me perform a little surgery because I see this all the time. It's a good idea for me to cut your knee apart and just like start repairing your ACL. Be like, no, what testing have we done? You have to do testing, right? So if we roll up to the ground, we can test the ground for excessive resistance by testing voltage drop on the ground. Okay, get what I'm saying? So if you voltage drop the ground, or you available voltage the ground and calculate the voltage drop, if you have, let's say, 2 volts going to that ground and you have 0 volts on the chassis, that means that ground is dropping 2 volts. That's a huge failure. Because remember, anything in the circuit should not drop really more than like a 0.2. All of the little drops should not be more than a 0.5. So if you're dropping 2 volts on a ground, you just measured that ground is defective, that ground is a problem. Then by all means, please unbolt it, clean it up, repair it, bolt it back up. And how can you verify that your new ground connection that's clean is good? Remeasure it, exactly. So with electrical stuff, we all naturally have been able to use our eyes to do a lot of things in the life up to this point. But once it's electrical, there's only so much you can do with your eyes. You got to get those tools and you got to measure stuff. And the measurements will confirm or tell you, hey, no, it's not a bad ground, right? If you measure it and it's good, it's not a bad ground, move on. Don't waste a bunch of time trying to clean it all up. And that's kind of what the point of this exercise is going to be today, is locating excessive voltage drop caused by resistance. So our voltage drop test is not focused on the 12 volts as much as it is like whatever the drop is, whatever the voltage is at that point. Makes sense? So in the vehicle, we can relatively assume that it's going to be a 12 volt system and it's about 12 volts unless all the electrical accessories are dead. Like we said, if it's a dead battery, you better be able to identify that quickly just by windows and lights and checking. If everything's slow and dim, don't start testing the circuit. That's a battery problem. Go check the battery out. Right, but assuming that the source voltage is good, if we're having added resistance, that's going to severely decrease our amps, right? If you think about that. The ohm pulling up on the rope, that's like corrosion, rust, all these various things, is really going to choke the amperage down to basically maybe little to nothing. There's 2 ways to look at it. The bulb is dim. The bulb is dim because the amperage is low, and that's true. The amperage is low because we have added resistance. We're pulling up on the rope. We're choking out the amps. And so low amps is going to mean a dim bulb. And I agree with that. But if you think about how we really measure it, we don't commonly want to just split the circuit open and measure amperage. And measuring the amperage can tell you some things, but it's not particularly effective at diagnosing where the added resistance is. Because if you recall, in a series circuit, if we measure amps, the amperage is going to be the same anywhere in the circuit. So you measure an amps at 10 different places, doesn't tell you where the added resistance is. Whereas when we measure voltage at different points, we can determine where this resistance is. So technically the reason the bulb is dim is because the amps are low. But the way I want you to think about it, which is also true but a different perspective, is it's because unwanted resistance is consuming voltage, leaving less voltage for the actual load, and that's why it's dim. See what I'm saying? If you think of it like that, that's gonna lead you down a better understanding of how to actually diagnose the issue, right? So as we jump in a little bit more, here's cleaning up a ground. We talked about that ground. That ground could be corroded, so we're wire brushing it. What do you think happened here? Doesn't that kind of look like it got hit? Remember I was telling you about that Duramax that had the really tight harness that went over this bracket? Well, that might have rubbed through, or maybe if it's under the car, it got hit by some, maybe the customer hit a 2x4 on the road and it came up and jammed the wires and actually damaged them, you know. So this is the type of stuff that we see. If this eyelet was corroded, that would be added resistance. Right here, I was looking at these wires. It looks like a couple of these wires might actually be open, but if they're not completely open and they're hanging on by a couple strands of wire, once we start really sending some current through that wire, that's going to get those 2-3 strands that are left, it's going to get them hot, and that's going to become added resistance. So this would be a voltage drop. Right now, it's pretty fresh. What do you think is going to happen over time when those are exposed to the moisture and the elements? Corrosion, yeah, big time rust and corrosion. And the copper itself doesn't actually rust, and aluminum either, but they do oxidize and corrode. And if you ever see a battery terminal that has that white chalky powder, that's oxidation we're talking about. The stuff will just look kind of like powdery. That would all be oxidation, which adds resistance, right? So these are the real life applications of kind of what we're talking about, and we can clean it up. And the other kind of pain is like sometimes when it's corrosion and bad connections and stuff, it's not always consistent. It can be intermittent. So intermittent meaning, let's say it's that bulb. You go out and you look at the bulb and it looks good. And then you hit a bump and then the bulb is dim. And you hit another bump and it looks bright again. And then you hit another bump and it goes out. And you're like, what in the world is going on with this? Those are actually kind of hard to test. Ideally, if we can get it while it's acting up, you know, while the bulb is dim or while the bulb is out, we can make tests right there and we can find the source of the corrosion or the source of the added resistance, which may be corrosion. But think about this. What if the headlight bulb is bright at that moment? You're going to do some tests. You already know what your tests are going to conclude. All your tests are going to pass. You knew that because the bulb was bright, right? If the bulb is bright, all the tests are going to pass. So sometimes if they say, yeah, well, once in a while my headlight flickers, I'll look at it and be like, well, it's working right now. And I'll start wiggling, banging, moving, flexing. And if I flex the wire right here and then I notice the headlight goes dim, I'll be like, oh, it's in this area. Exactly what it is, I don't know. But then I can a little further look into a specific area. Remember, you may have 10 plus feet of wire. You can't really justify cutting all this conduit and all this. See this black stuff right here? Sometimes I call it conduit, and that's one way to call it, but other times wire loom. But all these wires are pulled together. It's interesting because I've actually seen how they do it at the factory. When they pull all those wires together, there's like a whole bunch of wires coming off little spools, and they pull them all together. And it's interesting because it's actually machines that are kind of similar to how they used to do some fabric making and stuff. So they'll say like a wire loom. They'll pull them all together and they'll put them kind of in a bunch, and then that's when they slide this black conduit protection plastic over the top of it. But sometimes the wires at the bottom could be maybe let's just say there's a red wire and then a blue wire and then a black wire on one car, but on the very next car, the blue wire may be at the bottom. So it's kind of weird. Every wire harness is not exactly perfectly identical because they're all being pulled in and then bound. So if you have a spot that's rubbing like on that Duramax, it may affect different wires on different vehicles because all those wires are pulled together and it's kind of messy. So if you think, oh, I want to check that wire because when I flexed it, whatever, if you want to cut that thing open, there's a whole lot of wires going in there. It's going to be hard to even find that wire in that big old mess because you're probably going to have multiple wires of the same color. So if you jump right in the middle of the connector or right in the middle of the harness and you cut it open, you're like, I'm looking for a red wire. You'd be like, oh, there's 5 red wires. Which one's which? I don't know. We have no way of really knowing what wire is which in the middle of the harness, which is why, it's kind of important that we do a lot of our testing at the right points and not just visual is not going to help you for much longer. Cool. And so I think you get the gist. I think you guys will recall we did this exercise last time, but just as a little bit of a reminder, if we want to do voltage and resistance, remember we're on the V and the ohms hole. Amps is the only one that's different because that goes through the fused part of the meter that has really no internal resistance. Okay, so like unless we're doing amps, just assume we're going to be in the V and ohms port. Pretty common. Right, and so like let's say that here we've got a basic circuit. I think this would be a good one to trace. And when I trace this, you should be able to come up with these numbers yourself. So let's say I go here, highlighter. Let's start with the red. Would you agree that this should be 12 volts? Ooh, that is not red. This should be 12, right? What about up to here? Should still be red? We agree. What about going through the fuse? Should be red. What about what's happening here? It's open. Okay, so if we're really being honest, if we look at this, we agree that the red should stop there because if you're picturing electrons as like little cars, they can't go past this point. There's no way for them to go past this. They're done right here. So technically, let's make the green ground. This would all be ground, okay? It would. That's just a matter of fact. But, if we're trying to test this thing, whatever it is, this resistor, let's draw it as a bulb. Should have done that in black. Let's close this switch. Now at this point, what should happen with the red? Should go through, right? Do you know what the A1 is? That's your ammeter. We're just showing your meter in line here. So now you can imagine if we're actually trying to measure through the ammeter, it should actually go through the meter, right? If your meter was over here, we'd send it into your meter and back out your meter. Get what I'm saying? So that's the correct way to measure amps. If it goes to the load right there, the load should consume all of the voltage, which should mean after the load, what should we have? Ground. I totally agree with that. That's 100% correct. Then, of course, this ground goes to chassis. All the grounds have to go back to the negative terminal. How does it get there? Yeah, so like you got the frame or whatever, metal or something, right? Your battery's grounded to the frame, and this bulb is grounded to the frame. So therefore, electrically, they're connected right there. Okay, so everybody knows. All right, that's one way to do this prediction. Now, another note, if you wanted to measure the voltage, you'd hook your meter up just like this, black right here. This is voltage dropping the load, the bulb. Red right here, okay? Your V1 would be your meter. If you want to measure resistance, you put your red right here, put your black lead right down here. But to measure resistance, what do we have to do? Yeah, make sure it's isolated. Make sure there's no electrons already flowing through that sucker. All right, I agree. Now, another way that you could look into this is, let's say that you didn't know what you were doing on this circuit, which is fine. You could be like, okay, where is the load? And I'd say, oh, that resistor, that's the load. Let me just go ahead and circle that. Now it kind of looks like a bulb. Now I'm less confused. Let's assume that our switch is closed. What I could do is I could say, wherever the load is, after that should be ground. Wherever the load is, before that should be positive. That's another way to predict your circuit, right? So when we roll out and do some more series circuit testing, you just look at the load, and before the load should be positive and after the load should be negative. So anything that's red, we're talking 12 volts. Anything that's green, we're talking 0 volts. Okay, make sense? Fair enough? Simple? Now that's, of course, your most simple of simple circuits, but that's fine. Now if we wanted to actually do math, and we can, let's go with, I'll keep it green, but we'll do a pen. If we have voltage of 12, we would have to draw this thing, right? You remember this? V, I, R. The voltage is 12. And let's just say we know the resistance. We would cover the I, right? So it would be V over R. So that would be, would you agree with me, 12? What's the resistance? 12 divided by R1. How would we know the resistance? You could measure it, right? Put your meter on there and be like, oh, it's 100 ohms. So 12 over 100, 12 divided by 100 equals 0.12 amps, right? So we're just reproving Ohm's law. Hopefully that made sense. Now let's demonstrate this very scientifically. Let's say you had a 100 ohm resistor, right? That's your bulb. We'll even draw it in there. Let's say unintentionally you end up with 100 ohms of extra resistance on the ground. If you're paying attention to the visual with the ohm guy pulling up on the rope, we went from, what was our resistance before? 100. We added another 100. What's the total resistance? 200. You should know, just based on that visual, what should happen to the amps right now. Yeah, like a lot. Kind of make sense? Visually, that should make sense. If you add resistance to the circuit, the amps are going to go down. The way we could diagnose is slightly different. So let's do the math. We have 12 volts. Remember this, we'll do this whole thing. V, I'm not going to make it I, I'll make it A and R. We have the voltage, and it's going to be over the resistance, right? Because of that arrangement. 12 divided by 200 be 0.06 amps, I believe. So the amperage went in half. You know why that makes sense? Because the resistance doubled. So it's very interesting. Things are very proportional. They make a lot of sense. Like the more I look at it, it's like, hey, that actually makes sense. That's why it's Ohm's law. You can predict it. Make sense? Cool. So we just proved mathematically if we add resistance, the amperage decreases. But that doesn't necessarily help us. I feel like sometimes the textbooks all get really fixated on the scientific part of it. So that way they can go to their, they can go to their teacher conferences and be like, oh yeah, I'm helping students in STEM because we calculate Ohm's law. I don't care. I want you to be able to get a job and fix the cars and make pretty good income and provide for yourself. That's what I care about. No, you're not going to do Ohm's law on the car. But there's that other law, Kirchhoff's law. Let me show you why that would help you. So you kind of understand Ohm's laws there, but let's go with Kirchhoff's law. Kirchhoff's law, if we recall, was, let's just give it a quick trace. That was not what I was trying to do. Trying to do a highlighter, and I'm trying to do red. Right, we'll just draw these, and this should be ground. But let's just say we unfortunately had a little extra resistance right here. So I'm going to only put ground here. And that section there is going to become a little bit different. So let's leave that one blank. Let's say that is because we had that 100 ohm. But let's draw it like this, okay? This is an unwanted resistor. This is corrosion on that bolt, on those threads, on that whatever. This is also 100 ohms. Okay, we know how that would work out in Ohm's law, but that doesn't really help us. So let's discuss what would we get on this measurement. Who thinks they know what we would get at, let's say, this point right here, if you were to do available voltage check? Or if the circuit was working, what should you get? You should know that. We should get 12, and the good news for you is in this measurement we did. What should I get down here? How many volts? We should get 0, but sadly we got 6. If you got 12 before the load and there's still 6 volts left over on the ground, I'm going to tell you that there's unwanted resistance on the ground. There should not be 6 volts on the ground. The only reason there would ever be 6 volts is because this load right here was 100 ohms. There must be apparently a secondary load down here that's also 100 ohms. That's the only reason that this area right here would be 6. It's saving half of the money for the sibling that's of equal size and strength, right? That's going to actually help you fix the car. Kind of makes sense? So how would I draw this on a diagram? Well, I mean, really this should all be green, but in reality right now it's kind of like a, I don't know, it's some intermediate voltage. Like we could make it some different color. But normally we'd actually just draw it and do the test, right? You all know we should have got 0 volts down here, but we got 6. Tells us there's something wrong. All right, what if it was slightly different? What if at this point we should have 12, right? But what if I got, sadly, 6? Why is there only 6 volts going into the bulb?
Something in the switch.
On the positive side. Exactly. If there's only 6 volts by the time it gets to the bulb, the problem was on the positive. But if there's 6 volts on the ground side, there's something on the ground, right? So with a quick measurement, you can determine is on the positive or is on the negative. So if this is 6 volts right here, maybe I back up here. What should I have right there? What should I have? Here at the switch. Going into the switch, I should have 12. Let's say I took one more measurement right here and I had 6. What's wrong? The switch itself. The switch is dropping, yeah, corrosion in the switch. Exactly. Now we're applying the real world application of like your switch has little metal, tinny little contacts in there, and they've opened and closed a million times. And actually, I literally just have a tractor at my house right now. It's a skip loader. It's a big tractor. And the neighbor, he's fairly smart, but he's more mechanically smart. It wouldn't start. He figured out it was the ignition switch. He put his own little toggle switch on the side. And that was like 5 years ago. And the tractor sits outside in the rain and in everything. And, we had that rain a while back. And he goes to flip the switch and power the tractor on. It won't work. He's like, hey, I said, hey, can I use the tractor? I need to move some rocks. And he's like, oh, yeah, no problem. But it won't start. I think there's a problem with the switch because I bypassed the switch and I ran power directly to the fuel solenoid. And I was like, well, that'll be our deal. I'll use the tractor and I'll fix it for you. Very simple diagnosis. I checked to see if there's voltage getting to the load, which happens to be the fuel shutoff solenoid, and there was like basically 0. So I went back to the switch. I found there was 12 volts going into the switch. There's 0 volts coming out of the switch. The switch is no good, like in moments. He's so thankful because it was like, he can see stuff, but he can't really measure it. He can't predict it. He didn't gain these skills, right? So for me, it was like 12 volts, 0 volts. Oh, your switch is bad. And I was even on the super cheap. I literally took the switch out. I pried little tabs open. I opened it up. I sprayed WD-40 in there. I sanded the contacts a little bit. I cleaned it all up. I put it back together, and then I used it because I really needed to move rocks. I really didn't need to go down to try to find a new switch. So I just really repaired the little corrosion on those contacts. Kind of makes sense? pretty quick fix.
So on something like a switch,
Yeah.
in an automotive context with like a car, like a window switch or something, you
Yeah.
replace the whole switch though.
Exactly. And technically I'm kind of cheating that situation mainly because my whole goal is to use the tractor to move the rocks. But when the customers come in and they have a broken car, the last thing you want to do is give them back something that's prone to failure. So like we don't usually get down to that level where we're doing contacts. It's just like you need a window switch, you need a whatever, multifunction switch, we don't have to do surgery on that because quickly a call away is like, hey, let me get this switch. Where it gets tricky is when people start to modify the cars, and that's why a lot of us will just say like, look, if the car's modified, we're not really going to get involved because you do some cool mods on your car. Did you make a new wiring diagram? Did you update your service manual, right? So it's imperative that I can follow the service manual and the wiring diagrams and do my testing quickly and get a part price. And I mean, it's not really even rocket science. Like if you find a voltage drop across the switch, it's a bad switch, and you're well within your rights to bill good diagnosis time, get a price on the switch, and the customer may or may not approve the job, but at that point, your job is done. Hey, I diagnosed it, it's a bad switch. Then the customer may say, well, that's it, I want to take it and do the switch myself. Then great, go, whatever, that's fine. But we don't have to get really that down and dirty. Just if it's a switch, sell it, done. Yeah. With his, I don't know where that switch came from. It was kind of a unique one. He had to drill a hole, so like I got to try to find a similar switch. And I could probably find it on Amazon, but I cleaned it up and we're going to run it. And if it fails again, they'll be like, hey, we really need to get a new switch, and you should probably get a switch that's more outdoor rated. That switch wasn't that watertight, which makes sense why it failed. Cool, so very good. All right, if you understood that, you should understand a lot of this type of stuff that we're about to get into here. All right, let's say, how about this one? It's a good diagram. We could do Ohm's law on this. It's probably going to be a little bit weird because if we look at this, where is the load? And this can be a little bit confusing. Isn't this the load? But then wait a minute, what's this? And this is where it gets tricky, is you have kind of like two in here. The LED has its own resistor because the LEDs operate on a very low voltage. So if you were to look at the R1 as 100 ohms, but then we've got a different resistance down here, that's going to make it a little bit more complicated. I'm actually trying to recall this one. Let's close the switch. If we're to trace it, what did you guys find easier, starting at the positive or starting at the load and drawing backwards and forwards, or what'd you think? We'll start. All right, here we go. We agree with this. And then can we agree with this? Then the thing that's weird is there's kind of like two loads in a sense. So anywhere in here, sometimes we'll call this intermediate voltage. Like I don't know exactly what this voltage is going to be in here because there's multiple. So it's a little bit weird. If we were to find the total resistance, we could figure it out. What we did on this one was a little bit different. If we did a voltage drop and we found that there's actually 0.2 volts down here, to 0, we could actually determine the second resistance, but I don't feel like that's really particularly valuable. So let's just say we looked at this. What voltage would you expect to be right there? 12. All right, so this is just like basically an LED headlight or LED tail light. You can't see the filament, so we'd go and be like, hey, does the LED have 12 volts? Yes. What should it have down here? Okay, cool. If we have 12 volts going in and 0 volts going out and the thing doesn't work, it's because the defect is in the LED tail light or headlight assembly. This part is no good. That'd be the simple diagnosis. But what if it was slightly different? What if we had 12 volts up there and we had 12 volts down here? Does it need a new LED taillight assembly? How does it have 12 volts on the ground? Is there a short to positive on the ground? There could be, but that's not likely. You know what's much more likely? Rust and corrosion. So if there's 12 volts on the ground side, what's that tell you is happening on the ground somewhere? You probably have corrosion in here. So you know what we probably don't need to sell? We probably don't need to sell a taillight, an LED taillight assembly. We probably do need to repair the ground, right? So this is just how you would diagnose a taillight that's an LED. Sometimes, again, the book will be like, oh, we need to figure out exactly what the amperage is and the resistance, but who really cares? Because your resistor and your LED with the integrated resistor, and this is actually the light emitting diode right here, we don't really care what the resistance is inside the circuit board. What I care about is the LED taillight assembly getting 12 volts here? And is it getting ground here? And if yes, great, it's a bad assembly. And if this is 12 volts, then the ground is the problem. But what if this was 0 volts? What's the problem?
The other side.
Yeah, something on the positive. What it is, I don't know. Then we'd have to back up here. What if I had 12 volts here after the switch, but I had 0 volts down here? That would be somewhere between this point and this point. That'd be like a wire repair, right? So we just got to sell the customer the right thing because the diagnosis is right. Go ahead.
Back when you said you had the 12 volts going into the assembly.
Yeah.
And there's 12 volts at the bottom.
All right, let's redraw.
How would the lights work?
They wouldn't. So that'd be the point. The lights would not work. The customers come in because the light doesn't work. And if you measure, we've got 12 right here, and then you measure on the ground and you're expecting 0, but you find you have 12 volts down there, you know why the lights don't work. It doesn't have a ground. The ground is not there. If the ground is, let's say you did one more measurement right at the chassis and most likely you got 0 volts. If you have 12 volts on the negative side at the bulb or at the assembly, but you have 0 volts on the chassis, that would be the wire between here and here is no good. Right, so we just need to do wire repair or whatever. Cool. Not sell a $300 taillight assembly. Please don't. Because that's not going to fix it. And we proved it. Oh, I got a couple more things to delete. Cool. And you'll notice we're going to do more similar types of things on this. Oh, you guys all got to do the diode check? That was fun. So if we're working with a tail light that's like a regular type of bulb, it's kind of cool because if you think it's the bulb, well, first off, honestly, you can pull it out, you could look at it like this. But if it's an LED, there's no filament, there's nothing to see. So if it's a bulb, you can check resistance and be like, oh, the bulb has 4 ohms, that's a good bulb. But if it's an LED, what can you measure? You can't simply put it on resistance. Like resistance would work on a regular bulb, but if it's an LED, did you catch what you had to do? You had to do the diode check, and the diode check is going to tell you how many volts it takes to actually push through the diode. We could test an LED like that as well. Sometimes it's one way to do it, right? So it's just more saying like if for some reason you want to double check yourself, if you got the voltages that we talked about back here, you have 12 volts coming in, you have 0 volts coming out, that means this assembly has everything it needs to work. But if you wanted to double check it, you can actually do a diode test and see, you know, if the diode is checking. So if we can go positive this way and it says it takes 0.672 volts, but then you flip it and you try to do it in reverse and it says, oh, well, that would be like a pass. That'd be a good diode test. Normally, I wouldn't waste any time on that. I would just go ahead and do my voltage tests. And if I have 12 volts here and I have 0 volts here and it doesn't work, it's a bad LED assembly. I don't go any further than that, but you can, just so you know. Now, we're on to the circuit types, which is where we need to be. And I purposely left a little bit. That was kind of review, what we did right there. A little bit of new information because we applied it really well, but none of that was particularly different. If we look at these different types of circuits, series, parallel, let's define the differences. All right, think of this as roads. If you leave home, you only have one road that goes this whole entire distance. So if the drawbridge is open, or if a car stalls right here, you understand this is the only road. In a series circuits, there's only one road. What do you think would happen if we had an open in the fuse? Would this bulb work? What if we had an open in this wire right there? What would happen to the bulb?
It wouldn't light up.
Correct. So Christmas lights, old school style. They were all in series. You had 100 bulbs, and if one bulb blew, you know what happened to all the Christmas lights? They all went out. And then, depending on exactly how well trained your parents were, they're over there taking one light bulb out and put a new one in, and another one, and a new one, and another one, and a new one. And they're just testing, trial and error style, until they take a bulb out and they put a substitute bulb in, and all of a sudden it fixes them all. They're just randomly poking for wherever the open is. Make sense? That's an example of a series circuit. If the circuit's open at any point, it's going to cause all the current flow to stop. All the bulbs will be out. New Christmas lights typically don't work like that. That was very frustrating. A lot of times the new Christmas lights, they make them at least a little bit closer to parallel. So let's look at a parallel now. If we had an open circuit right here, what would happen with the bulbs?
One bulb.
Exactly, right there. You got it. So if we did it like that, and I were to trace this circuit, this is the first time you've seen a parallel, so we'll trace the parallel. Positive, right, through the fuse, assuming the switch is closed, down, goes, and goes, and then grounds and grounds, okay? This is not really a difficult thing to understand. If you had a lane closure over here, that doesn't affect over here. That one is still open, so cars can still go through the bulb. So you still have one bulb. This is your headlights. Your headlights are wired in parallel. You know that if one headlight fails, it doesn't take out both, right? They're wired in parallel. Imagine if they were to wire them in series, that'd be scary. The second one headlight blows, you have no headlights at all. That's not a good idea. That engineer would be fired. So parallel is very common. What if we had an open right here? Again, that would only take out this bulb. This bulb would still be okay. Cool. So that's your parallel. And don't worry, we're going to cover parallel some more. We're really mostly going to focus on series because here's the justification. If this bulb is in op right here, only that bulb, do you think that it could be the switch? Keep in mind, this one works. Do you think it could be the switch? No, because wouldn't that make both of the bulbs in op? So if only one bulb is in op, this is what I can tell you. It's between here and here. So it's got to be something like this. So then if I were to extract that out and bring it down here, I know that it's from this to this. That's it. Didn't we just draw that out? That was here. If I know it's between those 2 points, I can ignore all of this stuff and just focus on this to this and be like, it could be this wire. Maybe it could be this little splice. It could be this bulb. It could be this wire. It could be that splice, right? So At that point, this thing down here, this is just your series circuit again. So if you have a problem on a parallel circuit, you really just determine where the fault is by your understanding, and then you pretty much just diagnose the series circuit anyway. You're not really diagnosing a parallel circuit any different once you break it down to just the series part. Cool? Okay, so what if we look at series parallel, and this will just be an introduction to series parallel. We'll cover it some more. Series parallel is kind of unique. This will be the first time that we draw this. This will be positive, right? Goes through the fuse will be positive. Goes through the switch will be positive. Goes to the dimmer. What the heck is the dimmer? The dimmer, FYI, is a load. So this is our first load. After the dimmer, how much voltage should we have? Well, the dimmer is a load, so it's going to consume something, but that's why it's a series parallel, because I don't know what the voltage is in there. What I can tell you is this will be ground down here. We're in agreement that this will be ground. This should all be 0. But right in here, it's going to be some sort of an intermediate voltage. Let's make it blue. How much volts on the blue? I don't actually know. Because you have electrons going through. Let me switch back over to black. If you have the electrons going through like this, some of that voltage is going to be dropped on the bulb. I mean on the dimmer. But how much? Depends on the position of the dimmer. The dimmer is a variable resistor. So I don't know how much, but if you want your lights really bright, you turn the dimmer like clockwise. Maybe this is just going to drop 1 volt drop. So you'd have a 1V. That would mean you had 12 here, you have 11 here. Then both of these bulbs have access to the 11. And then after that, you'll have a 0. So each of these bulbs were able to drop their own 11. It's a series parallel because it has a load in the series part, right? So if you look right here, where it says series, I think you can agree, getting there, this part right here, this is all series. This part down here, this is parallel. That's why it's both. There's a series part of the circuit and a parallel part of the circuit. Now, if that's true, wait a minute. Isn't this a series part? Kind of. We can diagnose it like that, but you know why this is all parallel? There's no load here. See that? If we had a load somewhere here, like this one does, the dimmer is an actual load. If you had a load in the series part and then 2 or more loads in the parallel part, that would be a series parallel. But see, over here, there's no load, so this is just straight parallel. Okay, that part was always a little bit weird to me. So truthfully, on the car, there's very little actual series parallel. The only one I could think of is the instrument panel lights where you adjust the dimmer. The dimmer is the first load in the series part of the circuit because it's going to dim all the parallel bulbs in your instrument panel and your radio and all that type of stuff. Cool? Now, if we were to apply just a bit on series parallel, what do you think would happen if I had a problem with the dimmer? If I had a problem with the dimmer right here, if this dimmer was open or high resistance, which bulbs would it affect? Both of the bulbs. Great. So that would mean if both the bulbs are affected, I pretty much know it's in the series part. I'm diagnosing a series circuit. What if I had one bulb out? Do I think it's in the series part? Because the series affects both bulbs. But if only one bulb is out, it has to be in the parallel part. And specifically, it would have to be in the part that looks like this. Because it's just the one bulb, right? Obviously, all this wiring must be good because the bulb is working, so I know it's only this part. So if we're diagnosing in the parallel part, we're still just going to look at what the symptom is and be like, oh, it's got to be between here and here. And then we're ultimately still just diagnosing that individual section as a as a series circuit anyway. It's kind of funny to think about. Now, everybody kind of understand the series and the parallel? Because we're going to spend most of our time on series right now just to make sure you're really dialed in on how to diagnose these. And then we'll actually diagnose some series, some parallel and some series parallel. All right, here we go. Basic, simple. See how it's already traced? Positive on the positive side, positive through the fuse, positive through the switch, positive to the load. And remember, at the load is where it should consume the voltage and leave just ground, right? So this one is pre-traced. It's one path. Here's Ohm's law, or even Kirchhoff's law, you could say. If we were to do Ohm's law, it would be, you remember that formula, V, A, R. How do we come up with the R on this circuit? FYI, the R is a total. So this R right here would be the total R, total resistance. How do we come up with the total resistance? R1 plus R2. Let's say this one was 4 and this one was 4. What's the total? 8. Exactly. What if we added another bulb and it was 4, 4, 4, 4, plus 4, plus 4? The total resistance keeps going up. Now remember, if the total resistance, it keeps going up, what's that going to cause for the amperage? The resistance, the guy pulling on the rope, keeps pulling harder and harder. It was 4, and then it was 8, then it was 12, and then it was 16. What's going to happen to your amps as you keep adding more and more resistance? Bingo, exactly. We could prove it mathematically if you want. You can keep doing the math, right? If we were to go from 8 to 12, 12 divided by 12 would be 1. But what if we were to have 24 as our total R? It'd be 12 divided by 24, and that would only be a 0.5, right? So at 12 ohms, it's got 1 amp. At 24 ohms, it's got a half an amp, right? The resistance that we add reduces the current proportionally more and more and more and more. Why do you care about that? Well, what if we add resistance not in the form of a productive and happy bulb? What if we add resistance in the form of unwanted corrosion? Remember that? The amps go down, right? And the bulb has to share it. So now let's, exactly, yeah. Let's talk about how the bulbs could be siblings. You had, back in the good old days, before, mom and dad had another child, you had one bulb. And this bulb got to consume how many volts? Oops, I was not on what I thought I was. Yay, 12 volts. 12 volts makes for a happy bulb. And then instead, mom and dad are like, hey, I know, we're fighting a little bit. You know what'll make it better? We'll have another child. And now, wait a minute. Bulb number 1 used to get 12. Now bulb number 1 has to share it. There's still only a limited amount of income. Assuming these bulbs are equal size and strength, what's each bulb going to consume? 6, and you did it again. 6 volts and 6 volts. And that's true for now because those are equal size and strength. Now, obviously, if this child was 5 and this child was 1, if it's a 5-year-old child, the 5-year-old's probably going to consume more money because the 5-year-old child's stronger, and the 1-year-old can't defend itself, so it's going to be left with less voltage to be consumed, is the visual way to how I picture it. It's also slightly disturbing, FYI. Okay, well, if that's true, let's think about, what if you're a truck driver and you like lights on your truck? And you want to add lights and make it brighter. Would you add them in series? Because every bulb you add in series, a third bulb is going to make the first 2 more dim. A fourth bulb, it's going to make them all more dim. A fifth bulb, it's going to make them all more dim, right? So if you add bulbs in series, it's just making them, they all have to share the limited amount of voltage. Cool? So what if you're a truck driver and you wanted to add bulbs and make your truck look really cool? How would you wire them? Parallel. See, over here, we could add bulbs. We could add bulbs. We could add bulbs over here. Like this. Another bulb and another bulb and another bulb. Okay, and each time we add one of those bulbs, you'll notice they all have access to the 12. They're all getting access to $12. Well, that means there's going to be a lot of cash flow. There's going to be a lot of amps, right? So if you keep adding bulbs in series, they're all going to be dim, but your amps are going to go down. But if you keep adding bulbs in parallel, you just added 3 lanes to that freeway. You think there's going to be more cars flowing on that freeway? Yeah, exactly. Which means, how overloaded is this fuse going to be? Make sense? So that's why you can't just add a whole bunch of loads in parallel, because you're still trying to send it all through the same fuse. I mean, that's kind of what we do around here. Build more houses. Don't expand the roads. Just build the houses first, and then eventually we'll get a little more tax money, and then maybe we'll add a lane or two. But later, right? So right now, our single lanes and that type of stuff are severely over congested. That's kind of like how we would add the bulbs, okay? So if that makes sense, now we can get a little bit more into the how we're going to diagnose it. Okay, pretty good. Here's a measurement for us. This is a voltage drop in a series circuit. It's already done for you, but let's go ahead and let me just add a detail to this. And let's just say, I don't want you to really know that this is a dimmer. Let's just say this is unwanted. You know what I mean by that? Like corrosion, that type of thing. Okay, let's trace it. Let's trace it in a way that maybe you like better. Here's the lamp, right? This is the load. So after that, this should be ground. Before the load, what should it be? Positive 12. All right, cool. That's what we should get. So what I should get, okay, if that's unwanted, what I should get, and right now I'm on a voltage drop, but let's just say it's available voltage. Let's just say I take this lead, I run the black one down here, I take the red lead, and I go up this way somewhere. What should I get available going into the fuse? I'm going to give you that first one. What should I get coming out of the fuse right here? 12. What should I get going into the switch? Come on, tell me. I'll give you a clue. I traced the whole thing red. So you know what I should get? I should get 12s all the way down here. And then after the load, I should get zeros. Try to make this green. Cool. So what I should get, if I had 12 here, had 0 here, that should, 12 minus 0 is 12. I should get 12 dropping across the lamp. Okay, if you follow what I'm saying, you'll see that makes sense. But instead, what we did here is we're voltage dropping things individually. If we voltage dropped the fuse, positive here, negative here, the fuse read 0.1, that kind of tells me I had 12 and then I had 11.9, right? You see how there's 2 different ways to do voltage drop. You can measure the voltage drop with the meter, or you can measure the 12 volts with the positive, jump the positive down here and measure 11.9 and be like, oh, it dropped 0.1. That was 10 cents. Make sense? So, get it? Okay, so 12, 11.9. If I did a voltage drop and I dropped across the switch, it dropped another 0.1. We'd be down to like 11.8. Then I voltage dropped this thing, this unwanted resistance, and my voltage drop was 4.7. Why would I be dropping 4.7 volts on the thing? I shouldn't be, right? I should be dropping 12 volts down here. But if I drop 4.7, why would something like a connector, let's say this is a connector, why would a connector be consuming 4.7 volts? Yeah, unwanted resistance, corrosion. There's something is wrong in there. You didn't see it, you measured it. And if you measured and it dropped 4.7 volts, you're like, no, something's wrong here. That's no good. That's only going to leave 7 volts from my lamp. And how's that lamp going to look? Dim, exactly. Yeah, bingo. Cool. And so that's basically the way to voltage drop and define unwanted resistance, which is causing the customer concern, which is a dim bulb, right? That's voltage drops being measured and voltage drops being calculated to be very similar. Cool? Not bad? Go ahead.
Is that how you're going to ask us on the midterm?
I could ask you like this, or I could ask you like this. And actually, a lot of times, you know, it's okay that it's personal preference. So if we run through this, we had 12, right? Then we had 11.9. How much dropped? 0.1. Then we had 11.8. How much dropped? 0.1. So if I were to ask you what's the voltage drop across the switch, you should know that it's 0.1, right? Because you can do it a couple different ways. You could literally measure 11.9 coming in, 11.8 coming out, and be like, oh yeah, I dropped 0.1. Or you could measure it like this, right? You could put the red lead and the black lead on each side of it and measure the voltage drop. Or you could stab the black lead down here and poke your way around with the red lead. I had 12, then I had 11.9, 11.8. Then I had 7.1, and you're like, what? 7.1? Why do I only have 7.1 volts on all this? There's unwanted resistance right there. There's corrosion. Like in this case, it's the dimmer. We draw it as the dimmer. Kind of makes sense? Do it either way. Either way is fine. It's kind of the same.
We can't just say like 12 volts there, 12 volts there. Did you want us to give a number?
Actually, 12 volts is fine because really in the grand scheme of things, we're not worried about the 10 cents. You know, technically this fuse could drop up to 0.2 before it's really out of spec. The only thing is, if it were to drop 0.2 on the fuse and 0.2 on the switch, and then 0.2 on the ground, now you've got 0.6 volts in just the wiring and the switch and the fuse. That'd be over the 0.5, you know. So like, we're not really sweating these details too much. So like, if I write up a technician story, I may not add all those. I'm allergic to work. I may not add all those details like, oh, it dropped 0.05 across the fuse. Like, it's good, it's fine. So if I say 12, 12, 12, 12, cool. But if we had 12 right here, and then across the connector you drop to 7.1, that's a very important detail. These little 0.1s, not a real big deal. That 11.8 to 7.1, very big deal. That's causing the whole problem in the circuit. So that's more what I'm worried about when it comes to the midterm. So today, make sure you guys can become bilingual in a sense. Voltage drop, available voltage. Voltage drop, available voltage. Voltage drop, available voltage. Same, but different. Same, but different. Cool. Now let's say the other thing is you want to start to maybe not trace it, but you could actually trace it. But at a minimum, start to get good at predicting your voltages. You know, so if I were to look at this and I were to be like, well, all right, so right from here, I could go highlighter, I could go red and be like, all right, if this is the load, I should have 12 all the way up. This is the ground, I should have ground all the way down. Now, technically, as it's drawn, there's a load number 1, so I would actually be like, all right, then I should have 12 volts going up to the first load, red. I should have ground after the last load, and in between, I should have some intermediate type of voltage, like that, right? So it start thinking like that. You could do some basic tracing, that's fine. But when we do actually wiring diagrams, it's going to be much more complicated diagrams. There's going to be a lot of stuff going on. So we're going to cover wiring diagrams separately. And then, again, amps in a series circuit, this is not the first time. I told you I was going to cover it a bunch of times, and we really can't. We really can't keep blowing fuses, so I think we're good now. I think everybody's there. There's quite a few, not one group, but basically like more than half of the groups had a little, they let the magic smoke out of the fuse, which must have been what happened, because before the magic smoke came out, the thing worked. And after the magic smoke came out, it didn't work, so the smoke must have therefore been magic. I bet if you could gather up every last particle of smoke, you could probably make that thing work again. All right, try it, let me know. All right, so break the circuit open, measure it in line, but make sure that if we were to trace the electrons here, they'd be like this. They have to go through the meter, and then they still have to go through the load or loads. That's what's going to make sure that your fuse doesn't blow. So if we were to mess this up and have the red lead, let's say we put the red lead here, and we put the black lead down here, that would mean the electrons, which would be blue today, would be like, oh, we can go into the meter, we can go, oh, we don't have to go through the loads, we'll bypass the loads and go directly to ground. Yeah, that's a short, and your meter's like smoked. Or at least just the fuse, which we can't do anymore. Okay, good. A little summary. Resistance, I think you guys should be good on. Break the circuit open, measure the thing individually. So the dimmer was one way to talk about it, but what if this was the connector? What if it wasn't the dimmer? What if it was the connector? Don't you see how you could actually measure the resistance of a bad connector and be like 16 ohms on a connector? It shouldn't have 16 ohms on a connector. So sometimes if I feel like I might be a little like my mind's been buzzing, I've been fixing too many problem cars, and I'm kind of crazy, I'll be like, well, let me just verify my concern. I already did the voltage drop back here, if you'll recall, right? Back here, we talked about, we dropped, whatever that number is, 4.7 volts on the load. If it was like in this form, 4.7 volts. I already knew that dimmer was bad, which could be a connector, right? But if just for the heck of it, I want to double check, I could actually try to measure the resistance across that connector, and 0.2 ohms should be like a good number, or whatever your meter is when it's just touching black to red with no resistance. So you really should use the voltage drop, but you can also double check yourself with resistance periodically. But just understand, if you do lean on resistance, that's only sending a very minimal amount of electrons through. If there's, corrosion, but there's a little bit of clean metal, those small amount of electrons won't really get too backed up as long as there's a tiny little part of clean metal. But once you actually activate it, like so, if we were to go away from the resistance right here, and we were to go more to like this, and we have a lot of electrons flowing, that amount of corrosion, when it's combined with a whole bunch of cars trying to get on the freeway, that could actually cause more of a problem. So voltage drop, like I said before, is like testing it dynamically. It's like testing it. It's like testing the freeway while all the commuters are trying to get to work. Whereas if you're going to test the freeway and you're just going to be like, well, let's disconnect it and make sure no other cars can get on here, and let's just send one car through and see if it can make it, it'll be like, yeah, of course, it worked until you put all the cars on there, right? So again, resistance is not a bad test, but just understand resistance is not testing it while it's under full load, which is why I really have to stress available voltage and calculating voltage drop are going to be, they're just going to illuminate much more. If you got a freeway problem, let it be during all the commuting and the busy times. Then you'll find out if there's really good traffic flow or not. Cool? And I think let's talk through this this is what we're about to do, and I just want to give you guys just a little bit of heads up on some of these. So if we built this circuit, you should be able to trace it. You're going to. If we built this circuit, how is it different? Right? You had one bulb, and you have two bulbs. If this bulb got 12 volts available and it got to consume all 12 volts, how much does this one get? If they're equal 6 and 6, that's true. What if we got this many bulbs? 4, 4, and 4. Yeah, that's correct. But there's, and I'm good with that answer. So if we were to look at this one, I know that everybody could trace this one by now and predict it. But I'm going to throw a little bit of a wrench in the mix. Let's say, in fact, I'm not even going to trace it. I'm going to ask you, currently, with the switch open, what should my voltage be available right there at test point D? Think so? Think so, huh? All right, ready to have your mind blown? That's very normal, by the way. Almost everybody gets stuck on this one, including I've actually spoken with instructors and had them try to argue about this with me. And everybody's opinion is relevant. All right, check this out. Here's your cars, right? Cars. Cars get to the load. The load is like a stalled car. But the thing is, up here, what do we have? So the cars will be like, hey, I can just go around this guy. But then they get here and the drawbridge is open, so they all stop right there. If you have an open down here on the ground, you'll have 12 volts at test point D, because all that positive will go to here. Now, a way to explain that through Ohm's law is, I don't know, let's say that this bulb is 4 ohms. 4 ohms. What is this? What's the resistance of that open switch, that open circuit? Yeah, OL, which OL, you know, is out of limits. Or on some meters, it'll show this, which doesn't mean 1. That means infinite, right? So now if you apply Ohm's law right now, if you have, this is like resistance, right? It's an open. The open is measured by a lot of resistance. You have how much resistance? Infinite, millions of ohms. And this has a measly 4 ohms. This has infinite power and strength. You could say the 12 volts is going to drop here, and this will drop like basically nothing. So therefore, the 12 volts will go to this point, and it'll basically drop because you have infinite resistance right there. The other way I like to really think about it is just really with the cars, to be honest with you. If you have a stalled car right here, that's no big deal, because the cars, the traveling cars, will slowly and surely work around it, and they'll go to where the toll bridge is open. All right, I agree. Now, what happens when we close the switch, though? These red ones, they're gone. All those cars are gone. But the cars that are behind, stuck behind the stalled car, those ones will still be there, right? So if we were to close the switch, then we're going to get totally different readings. All right, so if we close the switch, let's make that official. Closed. And then if we were to switch back over, let's do the red. Yes, I agree. Red will go to there. The load will consume the voltage, and then all this would be ground, which is what most people visualize and most people think, and you're correct. But while there's an open on the ground, the positive will actually be on the black wires, if you will. The positive will go all the way to where the drawbridge is open. All right, cool. Hopefully that helps, because that, I always see ASE trying to trick people. They have an open ground, and it's always like, what the heck? How can there be 12 volts on test point D or E? Kind of wild. All right, if that's true, what about this? What measurement should I have on, let's go with test point, well, let's once again go with test point D. What voltage should I have right there? Think so? If your only options are 12 and 0, you ain't going to get this one. Because look, isn't this a load? And this a load? Let's say it's 4 ohms and 4 ohms. Parents pass down the 12. Very well. They pass down the $12. Here you go, kids. You're rich, $12. And you're like, oh, wait, I forgot we have twins. How much do they get each? All right, so then this one would drop 6, which would leave how much at test point D? 6 left over. But how much would be at test point F? No, oh, I forgot to close the switch. You know what? If we didn't close the switch, there would actually be 12 all the way through, because this switch would have ultimate infinite strength, right? So let's close this. Stop it with that. Let's close the switch. We should have 0 here, right? At this point, there's no more loads to consume. It should be all ground after the last load. Okay, makes sense? Should be. All right, if you didn't get that one, that's okay, because guess what? We got one more.
Why would they put the switch behind?
I'm not sure that I can give you the facts on that, but I can tell you some of the things that I've heard. A ground side switch is fairly common, and if you think about it, it all really depends on really like how you want the circuit to work. But in some ways, if you've already got the fuse up here and the relay and the thing and the whatever, and let's just say you send positive to all these, you could put the switch on the bottom just as easily. But someone once told me that ground controlled circuits, the switch lasts longer, and that didn't totally make sense to me, but I heard it said. I can't really verify it. That'd be a good electrical engineer question. The other thing is, remember now a lot of things are computer controlled, so this wouldn't be a switch. This would be more like a transistor, if you think about it. If we have the fuse box powering the bulb, but then on the ground side, we have the ECM controlling a bunch of the grounds, it probably makes a little bit more sense rather than taking the power, going to the fuse, then going to the ECM, and then leaving the ECM and going to the bulb, and then leaving the bulb and going to chassis. It makes a lot of sense for that fuse box to go directly to the load and then have all the grounds go to the ECM, and the ECM can control the ground side maybe a little bit better, I guess. But truthfully, those, sometimes you ask somebody and they're afraid to tell you, I don't know. I'm not. So that's what I've been told by some people who at least allegedly know more than me. Truth is, I really don't exactly know. But it works just as well, right? If you want to control the positive, no problem. But if you want to control the negative, no problem, same effect. If we open this switch, these lights go out. If the switch is over here and you open it, the lights go out. It works really just the same. Cool, so this is all ground side control, which is throwing you off. What about this one? What should I have at test point D?
Was it open or closed?
I need to make a mental note to always, we could test it which way you want it. I'll give you a clue. If it's open, 12 volts goes all the way to this point, right? And then this would be ground. But if we're going to really test this circuit to work, let's go with the switch closed, because that way we can actually test it. What do you think we have at test point D? Better yet, how about test point C? We got a disagreement. So if the parents handed off $12, has anybody spent any money by the point we're at C? C will have 12. Then at test point D, I don't know. Let's just say it's 4, 4, and 4 ohms. They're going to split it up 3 ways, right? So if the first child takes 4 volts, we would have a voltage drop of 4 volts if we do this. But what's that mean is left over on test point D? 8. What about test point G? 4. What about test point I? 0. Yeah, exactly. Yep. That'd be predictable. Now, unfortunately, that's the last productive or good working circuit. You know what? Actually, I should redo that. On this next one, Let's see if this will line up. I don't recall. Yeah, it does. On the next one, we try to put 3 bulbs in there at 4. Can totally trip this out. Let's go like this. 4, 4, and 4. But let's say this one is, let's do this one as a 12. This resistor as a 12 ohm. All right. Now this is going to be kind of weird. And you're going to do all these experiments, but right now we're just predicting together. Do we agree that this should be 12? Okay, to the first load. Also, after the last load, we agree that this should be ground because the switch is closed. Anything in between, I got to tell you, I don't really know. We'd probably draw it as like some intermediate voltage, right? Then you have to look at this and you have to be like, all right, which is going to drop which? What's the total resistance? 4, 4, 4,
24.
and 12. It's 24. So kind of the way that I would cheat through this is I would take that 24 as a known thing. If these are all 12s and this is a 12, at the midpoint, shouldn't this be a 6? Right? Because 4, 4, and 4 equals 12, and 12 is obviously 12. So therefore, at this point, it's going to be a 6. We can just tell that mathematically. Which would mean if this thing's going to get 6 because it's worth 12 ohms, and these, all 3 of them are going to get 6 because they're all combined worth 12 ohms. You see how we got there? How much are they going to split each way?
2, 2, and 2.
Yeah, exactly. So we'd have coming in, and so we could draw it like this. This would take 6. This would take 6. This would be 2, 2, 2, which would mean 12. 12 right here, 10, 8, 6, and then this would be 0, right? So first we could continue and continue and continue, but we don't really need to because I think you get the gist of it. And you're also going to do these as experiments, which is going to be fun. What about this? That's going to totally blow your mind, isn't it? What if we do this one with the switch open? Let's see what you know. Okay. What I'm going to do is I'll talk you through what I know. I think this is going to be positive until it goes to the first load. Let's talk about the grounds. I think this is going to be ground. But then look, the switch is open. So I don't think ground is going to go here. Ground is not going to go there because the switch is open. However, look at this one. Ground is going to go here. So now if you see what's got 12 volts in ground, what do you think the status of these bulbs is going to be? This bulb will be on. This bulb will be on. What about this one? It won't. Correct. Why?
You shorten the circuit.
I definitely shorted the circuit, but I want you to tell me why will these 2 bulbs work? Lamp A and lamp B will work. Why won't lamp C work? It doesn't have ground. That's only kind of true.
That part's not a complete circuit from there going down.
In a lot of ways, it might not really have any access to voltage either, right? So if we were to trace this, you got electrons, and electrons are doing their thing. Yeah, and you're right. This one's going to drop 6 volts. This one's going to drop 6 volts. And you'd be like, you know what? Similar to students, let's take the path of least resistance. Yoink. Right down here. Don't care about you. We're not going over there. That's just the way it's going to be. Right? So if you were to short that out just where it did it, test point F, I'm very confident that C and J are not going to work. Then if you think about it, if this is ground, which is not red, if this is ground, doesn't that make this ground? So really lamp C has ground right here. That means in a way the ground is actually going to go all the way through and just sit right there. This whole thing, if you measure on your meter, is actually going to seem like it's grounded because we shorted a ground on the test point F. Kind of a fun one. And we'll see. If I'm right, when you do that experiment, you're going to get the measurements we talked about. And if I'm wrong, you can come take my job. I'll give it to you right now. You could have it. All right, so like that's just all the experience will do. So we talked about if we go to do troubleshooting, let's say both of these bulbs are in-op at this point. What would make these two bulbs not work at all? These are totally not working. What are your thoughts? Give me a list of everything it could be.
Well, the switch is open, but it's not.
Yeah, but it could be a bad switch, right? Could it be a blown fuse? Yeah. Could it be one bad bulb? Would one bad bulb make both bulbs not work? Yeah. Could it be the other bad bulb? Could it be both bad bulbs? Could it be a bad ground? Could it be this bad wire? Could it be that bad wire? You see, so when a customer comes in, they say, my bulb doesn't work, what's wrong? I'm like, I don't know. It could be like all this stuff. I don't know. How am I going to know? How would you determine the cause of these bulbs not working? Give me one measurement you'd like to do. The answer is measurements. Give me one measurement. Where do you want to check? Let's do available voltage. Where do you want to check? You can make it up. You probably can't diagnose this with one measurement, by the way. Okay, so let's say right here. What if right there I had 0? What's that tell me about the circuit? Then I know it's over here. Exactly. Bingo. So that would leave like this wire, this fuse, this switch, this fuse, this wire, right? So in one measurement, right there, you guys did pretty good if you picked that spot. That splits most of the circuit in half. You could do it like this. You could think logically and you could be like, oh, well, I want to test right here. And if this has 12, what have you eliminated? You've really eliminated this. That leaves all this. So a lot of times we kind of want to like split the circuit if possible, but then you also have to think about how hard it is to test that point. You know what's pretty easy to test? The fuse. What if I tested right here and I had 0? Could be, but what if I had an open wire here? It would have 0 volts there. So with one more measurement, if I were to test right here and I were to get 12, then yes, it would be the fuse. Exactly. Right? So just really pointing out to you that if you understand and you know kind of where to take your measurements, next thing you know, you can do actual diagnosis and you can tell, hey, I know what's wrong with it. Not like I think it could be the thing. It is because I measured. All right. So if we have an open and you were to draw it and you were to voltage drop this, right here we're not measuring available voltage, we're voltage dropping. Why do you think we're getting 0 volts, 0 volts, 0 volts on the voltage drop in this instance? It's accurate, but why? That one was always kind of weird to me. Well, what if we draw it? Wouldn't you agree that 12 volts should come down? And when's it going to stop? Right there. How come? Because it's open. Then what are we going to have after that? Ground. So what's the difference between 12 volts and 12 volts? 0. 12 volts and 12 volts, 0. When you have an open, it's interesting. A lot of these things on the positive, they'll have a 0 volt drop. But then when we go to measure the wire after the dimmer and before the bulb, what's this drop going to be? Exactly. So you'd be like, hey, I dropped 12 volts on a wire. That would tell you that the wire's open. Right? Yet another way to diagnose the failure of the circuit. So what if we were to not voltage drop it? What if we were to do available voltage? Well, remember voltage drop is where we use the meter leads like this. Test, test, test. Available voltage is where we do it like this. Hang the ground in the negative terminal and then poke, poke, poke. So this is a different way to do it. We do available voltage right here. And I drag it up here, and I get a 12 volts, right? Then what if I drag it down here, and I get a 12 volts? How much voltage did that fuse drop? Hey, isn't that kind of like what we measured on that last page, right here? 0 volts? Yeah, that's correct. Then what if I drag it over here and I get 12 volts? That means the switch drops 0. I drag it over here and I get 12 volts. Cool. I drag it over here and I get 0 volts. What was the drop between the dimmer and the bulb connector? Exactly. And guess what? That was what we got on the last page too. That was a 12 volt drop. Remember when we drew that? Cool. So how do you want to diagnose it? Available voltage or voltage drop? Both are fine. The split half method is just saying it's sometimes makes sense to just like get to the middle of the circuit. Because if you get to the middle of the circuit and we have 12 volts, what do we know at that point? If we have 12 volts at that point, we know all this stuff is okay. We know this stuff down here must be no good. Make sense? You in one test, you were able to eliminate more things, so that means that was a more productive test. You could, if you wanted, test it, any number of different places. You could test it right here. What if I drug the lead up here and I measured 12.6 right here? That tells me nothing about any of this. Well, it tells me something down here is bad. I would have only verified that right up here is good. That doesn't make any sense. That's not a good productive test. Although sometimes I do it too. Okay, make sense? So real quick, you figure out which side of the circuit's on. You leave a little bit less to check. Okay, these were all for opens. Did we agree? These were all open circuits. Available voltage, or we could do voltage drop or available voltage, whatever. How else can we check for an open not using voltage? Don't just read the words, by the way. Yeah, exactly. You could put on ohms. You could check the resistance. And now this is something I've mentioned to you, but I want to re-mention it. What the heck is continuity? Continuity would mean your meter sends electrons out, and those electrons are able to make it back. That would mean there's continuity. Good continuity would be like 0.0 or 0.2. That would be good continuity. Good continuity means low resistance. Kind of make sense? You want to call it a continuity check? You can. That's fine. But you put it on resistance to do a continuity test. Now, if you really wanted to do it nice, you can put it on resistance and push this little button that looks like a speaker. And when there's good continuity, in other words, low resistance, do you know what the meter will do? Beep. And so if you were like trying to find one end of a wire and another end of a wire to see if there's a good connection, you get put it on that continuity test where it'll beep and touch the wire and not even have to see your meter because the meter's up here and you're up under the dash upside down and you're like beep. You're like, oh, thankfully that wire has good continuity, which means it has low resistance. Make sense? However, this one read OL. So what's that tell you?
Got a lot of resistance.
A lot. So that's an OL, out of limits, as good as an open. Infinite resistance, very high resistance. Like you might get like 300 mega ohms, remember? So that'd be like 300 million ohms. That's much different than 0.2 ohms, right? So another way to test for opens. But I can't stress enough, this is not really testing the circuit under load, so you might get one that looks like it's okay with a resistance or a continuity test, but if you actually test it with full amperage flow, you might be like, whoa, there's a big voltage drop there that I didn't catch with resistance. Make sense? Okay, a short circuit. The heck does that even mean? Well, does this circuit look short? It looks shorter than it did. Let's trace it. We agree that we should have 12 volts, right? 12 volts. 12 volts to the switch. 12 volts should go down, but what if instead we have ground? You know, technically when you draw a circuit, your red should never touch your green, right? So on a good circuit, the red would go like this, right? The red would go to the load, and then the green, I'm ignoring the dimmer, and then the green would be after the load. But you notice, The red doesn't exactly touch the green. There's a load between the two of them. That'd be a good thing. But like in this case, the red peeled off and went here, and the green is chassis, right? So you have, when you have red touching green directly, that's not good. What is the resistance of this circuit as it's drawn? How much resistance should the fuse have? Like nothing. The switch, like nothing. The wire, like nothing. So wait a minute. The whole resistance on here is very little. Well, let's do the math that we are supposed to do. Remember, V, A, R. The voltage will be 12. The resistance in this case will be 0. But because 0 is kind of weird, let's do 0.00001. Or maybe for simple math, let's do 0.01. Does anybody know what 12 divided by 0.01 is? Let's see, 12 volts. Oh, I have to actually use this. 12 divided by 0.01. 1200. Would you like 1200 amps? I can give you 1200 amps. How do your wires like 1200 amps? They don't like 1200 amps. Make sense? Exactly. But the only redeeming factor, the only one, is what do we have in there that's going to prevent that? See that fuse? Poof. Now you understand mathematically why the fuse blows if you have a short circuit. Make sense? Before, we were supposed to have some resistance right here, but we don't have resistance because we have a short circuit. Make sense? So this is specifically a short to ground. You shorted the positive to ground before the load, that fuse is going to blow. You could put a new fuse in it. You know what's going to happen? That fuse is going to blow. Then you'd be like, well, maybe I should put a bigger fuse in it. And if that fuse can handle more amps than the wires, now the wires are going to blow, which means get hot, light on fire, right? So now mathematically you can actually understand exactly why that happens. Okay, cool. Now how do we isolate it though? And this is part of your diagnosis. If you wanted to isolate, this is trippy, okay? It's actually really simple, but it just seems weird. So let's just say, you notice the fuse right here? We took the fuse, we took it out. What did we put in place? A headlight bulb. This is crazy. But if you put a headlight bulb in, did you know that headlight bulb is going to glow? How come? Well, think about it. You got positive right here, right? And right here, didn't we agree that we have a short to ground? So technically, isn't that headlight bulb getting 12 volts right here and ground right here? So that headlight is going to glow. It's going to glow, baby, glow, because it's got 12 volts and the short to ground gives it ground. So if we have that headlight glowing and I go down here and I disconnect right here and the headlight turns off, where does that tell me the short is? You missed it. If I disconnect right here and the headlight goes to off, what's that tell me about where the short is? That tells me the short's got to be down here somewhere. All right, cool. But let's say that I leave this part connected and I disconnect this and the headlight is still on. That tells me the source of the ground has got to be between here. It's got to be above there. Make sense? So if I disconnect up here and it goes away, but then I disconnect down here and it stays lit, I know it's between this point and this point. That kind of makes sense? So if I were to visualize it, I would say, hey, the fuse blew. Put the headlight in and just disconnect things until the headlight goes out, right? If I disconnect point A, it stays. Let's say I disconnect point A, it goes out. I disconnect point B, it goes out. I disconnect point C, it doesn't go out. I know that it's before C. Make sense? Kind of, sort of, ish, a little bit. That would tell me like, hey, it must be before that. Because once we disconnected here at the dimmer and it didn't go out, that tells me the source of the ground is not coming from down here. It tells me it's before that, right? So we just go step by step and disconnect things. Kind of makes sense, sort of? That's how you diagnose an actual short to ground, which is a good thing to know because you're probably going to have to do that. Okay, let me skim this because a lot of these I have pretty mathed, quite a bit of math. I just want to gauge it. Yeah, so we're going to do some really fun math, and I think you're going to love it and also kind of hate it. But I'm pretty sure the gist I get is you guys seem to be following pretty well, so I don't think this will be that tough. Here we go. All right, if we have 12 volts, this is just one way to measure voltage drop. Let's say we want to determine, I think what I was going for there is, yeah, what each reading would be. So if we look at, let's say, can you guys see V1 okay? V1. Whoops. What do you think V1 is going to read? Can you see V1? That's a voltage drop. Yeah, bingo, 12 volts. Good. So let's do V1 is 12. What do you think V2 is going to read? Yeah, I agree, like basically 0. Let's do 2 equals 0.1. I like that. Okay, now this is as the diagram is drawn. What do you think V3 is going to read?
11.9.
Now, why is that the case? Should we really drop the whole voltage across the switch? If it's open, basically, yeah, shouldn't we? We should drop, probably technically, yeah, this would probably be a straight 0. And this will be a 12. All right, I agree with that, which means how much should we drop on V4? Well, we've already dropped the 12, so isn't there nothing else left? All right, so we think 12, 0, 12, 0. That's what we think, right? I think I might agree with you. 12, 0, 12, 0. That was correct. So that was a little bit, we were on A. A, V1 is 12. A, V2 is 0. A, V3 is 12. And A, V4 is 0. 12, 0, 12, 0. We got that perfectly correct. Nice job. Now, we're going to do new numbers. Because we're on, now this was A. Up here was A. Let's do B. What changed on B? Switch is closed. Okay, very good. So just make sure you know that. V1, what do you think? I agree. V2, what do you think? 0-ish or 0.1 or so. But yeah, I mean, I'm good with 0 or 0.1. They're basically the same thing. It doesn't really matter. So 0-ish. What about 3? 0-ish on the switch. I agree. What about 4? 12-ish. Now let's explain. Remember, in Kirchhoff's law, the sum of all the voltage drops will equal the source voltage, right? That's why we measured V1. V1 is the source voltage. We agree? And the source voltage was 12. So therefore, we know by the time we get all the way to ground, it's going to have dropped 12. It's all about where it's going to drop. Now we know it's going to drop 12. Where's it going to drop? It should drop nothing on the fuse, nothing on the switch. It should drop the full 12 on the load, which I agree with. So this will be B, B12, B1, 12, B2, 0, B3, 0, and I think I cut off B down there. B4 should be 12. So yes, you guys got it. Very nice. Was that difficult? It shouldn't be, but if you can understand that, you're actually in pretty good shape with where we're at right now. There we go. B on 4 was 12, and also the total was 12. Okay, pretty simple, I think. Okay, now it's going to be worse, though. All right, if we look at the top one, V1, what do you think? I agree. 1 should be, whoops, I keep forgetting to change over from the pointer to the pen. V1, I agree with 12. V2, 0. V3, 12. And so you know the rest is going to be 12. Okay, we don't even have to check the answers. I can tell you you're correct. All right, if that's the case then, and that one was kind of a freebie, you all understood why, right? If the switch is open, it's going to drop the full 12 and everything else is going to have to drop 0. All right, but what if we're down here on B? What do you think about V1? 12 for sure. V2, essentially 0. V3, so far that's review. Now I'm going to write 4, and 5, and that's going to be a little bit weird. How do you know?
Because they're both 3 ohms.
Yes.
Share the same amount of voltage.
Bingo. Bingo. Now you're really proving to me you're there. So everybody understands there's going to be a 12-volt drop. We determined that based on the last problem. But in this case, you have 2 siblings of equal size and strength that are going to share that allowance money. It's going to be 6 and 6. We don't need to look at the answers. We know that's the answer. So good job. That one wasn't that tough, right? Well, let's see if I can hurt you. Here we go. Whew, here we go. All right. V1, you know what? Let's stop with this open switch thing. You know what the open switch is going to cause. It's going to be 12, it's going to be 0, it's going to be 12 and 0 because the switch is open, right? How about with the switch closed? V1, let's do it like this. V1, 2, 3, 4, and 5. V1, 12. V2, still 0. V3, still 0. How about 4 and 5, though? 4 and 5 are the only new ones. And is that kind of interesting? Because this is 4 ohms and this is 8 ohms. So if you were to run Ohm's law, 12 volts divided by 12 ohms is 1 amp. It's kind of, this is an interesting number that they've chosen. The fact that we have 12 volts means we know we're going to drop all 12 and it's going to be proportional to the resistance, right? So if you think about that, this is half as strong and this is twice as strong. And it has to equal 12, right? So I can just think in my mind, like if it has to be 12 and one has to be double, well then yeah, maybe this one is going to drop 4. And this one's going to drop 8. Is 8 plus 4 12? Is 4 half of 8? Is 8 double 4? Yes, so in all that mathematically equates. That all makes sense. These are correct answers. How could we do it the long way? Well, I showed you last time really with Ohm's law, and honestly, calculating Ohm's law is going to be a little undervalued from here on out. Okay, cool. So we are good. 4 ohms and 8 ohms, just so you can know that the answers are correct. Now 4, I think 4 is the last or is 5? Oh, 6 is the last. Okay, 4, here we go. No, did we just do 4? Didn't we just do 4, or am I tripping? 3, 4 and 8. 4 is, we did, you're right, 4 and 8. Okay, yeah, this one's a little different. You're right. Let's skip the open switch. Let's go directly to this one. How about 1, 2, 3, 4, 5. 1, do we still agree it's still 12? 2, do we agree it's 0? 3, 0. So we're at 4 and 5. Do these numbers look the same or different?
They're switched.
They're switched. So do you think that because sibling number 1 gets the pay first, it's going to drop 4 and then the other one's going to drop 8 or what? No, it's going to be 8 ohms is double the strength. So 4 this time is going to drop 8. 5 this time is going to drop 4. You understand the point there is just so you know, it doesn't matter what order they're in. It's all about their resistance is going to consume the proportional voltage. Whether one's first or the other one's first, the order doesn't matter. Kind of makes sense? And those numbers are correct. But wait, there's more. I think this one gets a little difficult from what I remember. Oh, dang it. This one's really going to be tough. The only good thing is I don't love math, so these numbers actually won't be that difficult. The concept's a little tricky. All right, so if we look at this, we know that V1, V2, and V3 are the same, right? So let's just focus on 4, 5, and now we have a new player in the game, 6. What do we think? What's 5 plus 5 plus 2? 12. So that makes our math easy because if it's going to drop 12 and it's going to be proportional to the number of ohms, that's exactly right. Isn't that funny? So 2 for V4. How come? Because it's got 2 ohms. V5, it's a little more than double, but luckily for you, the total being 12 ohms means we can just use the 5 ohms. And then 5 ohms, it's just the 5 ohms. Why are 5 and 6 going to drop the same? They have the same resistance. Yeah, so that's the same size and strength sibling right there. And then you have a little sibling here. So maybe you have 2 twins that are 10 and a younger sibling that's only 4 or something like that, right? But you could do it the longhand math way, but if you understand the point and the concept, we're great. Cool, so not that tough. Alrighty. So how about series circuit number 6? All right, this one is, what are we measuring here? Do you see V? No, there's no V. So what are we actually measuring? It's A. I can probably zoom in and not mess this up. I think we're good. All right, so if it's A, keep in mind this is a series circuit. Next week, by the way, we're off a series and we're on to parallel and series parallel. So series, this is pretty easy on a series. In a series circuit, I'm going to tell you that the amps are the same throughout the circuit. So this is where it gets kind of weird. You're thinking you got a big voltage, a small voltage drop and a big voltage drop and a really big voltage drop and this proportion and that proportion. With amps, none of that matters. The only thing that matters, we'll start with the closed circuit one because that's the only important one. We're going to have to do some basic Ohm's law, which I'll do right over here. V, A, R. The R is the total resistance. What's our total resistance? 6, 4, and 12. Okay, so if our voltage is 12, our total resistance is 12, our amperage is what? 1 amp. And if you understood what I said, how many amps are at A1? 1. How many amps are at A2? 1 and 3. 1 and 4. 1 amp. It's all the same. Now that's not going to be the case on series parallel or on parallel. But it is the case on series. It's all the same. So that one looked kind of intimidating, didn't it? I even might have got myself a little scared. But then when you look at it, it's like, oh, never mind. We're just measuring amps. And I believe I put an answer key on there. 1 amp, 1 amp, and in a shocking turn of events, 1 amp and 1 amp. Now where we'll pick up next week is going to be parallel, but not for today. So you guys did it. Very nice job. Very fun time that I had with you. What we're going to do right now is